Should I wait for the people at the back to sit down?
Yeah, why not?
Gregory, why don't you sit down? You're making me nervous.
There's plenty of space here. He's a big brother. He watches everybody.
It makes me nervous pacing up and down at the back.
What was supposed to make you? Okay, yeah.
Okay, all right. Thank you, Shi. Now, unlike the last time, I am a part of the program. This is mostly a commentary on the work of Victor Yacourt, Jörg Schumacher, P.K. Young, and Diego Danzis. So I have very little by way of original remarks to make. As somebody whose natural inclination is to make an experiment than a simulation when confronted with a problem, I am often dismayed by the fact that I cannot take advantage of such extraordinary changes that have been taking place in my own lifetime. As a function of time, you look at the brightness of synchrotron radiation facilities, for instance, it's gone from 10 power 9 to 10 power 25. So it's an enormous range in power of certain machines, but still people in turbulence cannot take advantage of such advances experimentally. I find it extraordinary. On the other hand, the computational people, you have seen this graph in different forms in this conference, where as a function of time the number of operations per second has changed in this fashion with these various machines. This is an updated plot prepared in about 2000 or so. You can see here the Earth simulator, which sits at the top, and then there are other machines, Blue Gene, Cray, Seeberg, which people have used. So I think this is an extraordinary change in power, but this fortunately has been put to use by the community as a whole, and my comments relate to the use of these things. And also perhaps of interest is how the price of the memory has changed as a function of time. See, if you were in 1950s, a gigabyte of memory would have cost you that much, whereas now terabytes can be had for a few cents more or less. I think things have changed a lot, and therefore it is natural that the turbulence people should be really interested in using the machine of this enormous power, machines of this power for their simulations. So for setting frame of reference for my comments, I take box turbulence, and the integral scale, the size of the box is of the order of the integral scale, maybe a few integral scales, and the number of grid points here is simply the grid resolution here divided by the length. It's inverse, let us say. You have the Kolmogorov scale, which is usually taken to be of the size of the box, and the microscale Reynolds number, which is of interest, I indicate by R lambda. Now I use here some sample authors, not because I want to criticize them, but because they are my friends and I value their work. If you look at these authors, the box size here, the grid size, as a fraction or a multiple of the Kolmogorov scale, has sort of been around 1. Roughly, some people have gone say 0.5 to 2.9, and the latest by Kaneda in this beautiful machine about varies from 1 to 3. So I sort of think of that as the standard resolution. If the box size is comparable to the Kolmogorov scale, maybe within a factor of 2 or something like that, I take that to be standard resolution. Now, as was shown earlier, if you say that the box size is comparable to the Kolmogorov scale and the box itself is of the order L, it's very easy to show that the Reynolds number, the microscale Reynolds number, you can compute out of this or generate out of this, goes with the size of this number of grid points to the power 2/3, 4.5 in fact sitting in front. This is what Ishihara called the other day as a different 2/3 law. This is a very simple calculation one can make. So that's the situation. And if you look at the size of the boxes people have calculated over time, I've drawn here a line, although there are points there which are scattered around it. The Reynolds number that you can compute in the boxes has varied as a function of time like this. The latest one, as I say, is from the Earth simulator, 4096 cube and 2048 cube in Seaborg. So it is like that. And the machine we are all waiting for very much is the petaflop machine, and there will be many machines. Many people are building these machines, and I have here data on who is building those machines if you are interested. So sometime early in the next decade we will have a petaflop machine, and you can extrapolate it and sort of say what kind of Reynolds number you can compute. And let us say we take this exercise here. At simulator n is 4096, and the microscale Reynolds number is the order 1200. The big Reynolds number is about 10 power 5. The box size to the Kolmogorov scale is of the order 1000 or 3 decades. And if you sort of extrapolate on a petaflop machine, you might probably want to do that. Whether one wants to do it or not, I don't know, but suppose you do that, you get a Reynolds number of 4000. The ratio is about 10,000 or 4 decades, and I am pretty sure it will happen sometime or the other sooner or later. And then the question is, when you have such scale separation, does it mean everything we need to know is pretty much known, and thereafter it is a question of just manipulating the data and spending some time on trying to look for fractal dimensions or whatever the heck you want. Okay, so that's the question. And unfortunately, I think things are a little bit more complicated, and that is what I want to bring to your attention. That's mostly the purpose of my talk. And if you have heard this before, as I have in fact given this presentation twice before in different places, please forgive me for it. And it's a trivial point in some sense. So now look at the energy dissipation as a function of position in the box. It sort of varies like that, and you go to an atmosphere or high Reynolds number of the sort that you are aspiring for in these petaflop machines. Now the energy dissipation is sort of like this, hardly anything most of the time, but extremely large levels at different times. So what is Kolmogorov scale? Kolmogorov scale is nu cube by epsilon to the power quarter. Normally you just take the average value of the energy dissipation and you get a certain number for the whole box. In reality, of course, there are these, if you look at the mean value of energy dissipation, this is really energy dissipation divided with the mean. It's sitting somewhere here at the very low level, 1 on this scale of few hundreds. So it's conceivable, therefore, that there will be scales, if you use the local value of the dissipation, that are much smaller than the Kolmogorov scale. In fact, order of magnitude smaller than the Kolmogorov scale. So in fact, there will be points or positions in the box where there is if you think of cascades, for instance, they go deeper than the Kolmogorov scale would sort of tell you. Of course, you have to imagine the physics to be a little different, but that's the main point of it. And so you can do this exercise, limit yourself to very low Reynolds numbers, and then not resolve the Kolmogorov scale, but 1/10 of the Kolmogorov scale, say. You can do that, use the big machine possible, as Jörg Schumacher did, and then you ask what is the probability density of the small scales in the flow, and this is the Kolmogorov scale, and you see, in fact, there is a very large number of scales, or a large part of the PDF on the left of this, so smaller than this. You can this is a trivially small Reynolds number, and he had to use only the small Reynolds number because he was demanding that very fine scales be resolved. And you can do that for the scalar as well, passive scalar. And again, you can see that this is the bachelor scale, which we all teach our students as one of the smallest scale in the passive scalar. But actually, there is a large part of the tail of this distribution. This only marks the peak of the distribution. So I would say then, smaller scales than eta, that is the nominal eta k is what I should have had, smaller than the Kolmogorov scale and the bachelor scale clearly exist in the flow, and this becomes more of an issue the higher in Reynolds number you go. At low Reynolds numbers, this is not such an important issue, but the higher you go, more ambitious you get, the bigger the machine you use, the larger the problem you will have. And so the question is, how much better should be the grid resolution for the discrete version to remain truthful, so to speak, or if you don't resolve it, what are you going to lose? So this is the answer, the question for which I would like some answers for. Clearly, you will lose things of the sort that Jorg was talking about in his talk yesterday, that is these singularities of two vortex rings hitting each other. I am not even talking about that, and that will take you very, very far and very, very deep into the resolution issue. But I am only talking about useful statistical data that we might miss. Okay, that is the question. And in fact, to show you that you don't have to be esoteric about the kind of things you miss, here is again Jorg's calculations, PDF of the energy dissipation, and this is for the standard resolution, 128 cube for this Reynolds number, whereas the same box, same Reynolds number, same everything, but resolved better by 8-fold, will tell you that the PDF is around here. If you are a theorist, for instance, trying to find what the tails of the distribution are, you better believe it. There is a big difference between the two, and there is really no way you are going to get the right distribution by just doing the simulations at the standard resolution. These are either the mean value or the standard deviation. I do not remember this. And this also happens in wall bounded flows, not just in grid turbulence. This is a picture, some version of this Jorg showed the other day. This is vorticity squared plotted here, and the probability density, and at different heights from the wall, 10, 30, 70 to 180 in wall units. And this is the standard resolution, standard meaning you resolve, as I said before, now viscous scale, for instance. You see that below here it's all garbage, and the distributions are in fact extended like this. And again, if you want to know what their if you have a theory you want to check against DNS, this will be tremendously important. And in fact, it is also important even for mean quantities, not just for esoteric quantities like the entropy and so on. And as a function of height from the wall, the Reynolds shear stress, you see there are two curves nearly similar, but with different resolutions, but they are not nearly similar if you are really interested in how these asymptotic values are approached. I think if you want a theory and you want to make a comparison with this, surely this is something you should pay attention to as well. So what should we do, and how will we know we have enough resolution, for instance? Let's take the typically structure functions of order 2n, and for very small r, all velocities are differentiable. Therefore, it will go like r to the power 2n. Therefore, if you have your structure functions calculated, normalized by r to the power 2n, and which is what you plot here against r, then if in fact there is a region in your calculated part which is flat, then I think you have resolved the part that is reasonable. Now, however, any chosen resolution at a fixed Reynolds number becomes increasingly inadequate with increasing moment order. You can see here at this Reynolds number, this is a fixed resolution. For instance, this here, that's a resolution, and the Kolmogorov scale is actually here. Now, for the second order, you have this much to spare, so to speak. But if you go to 10th order, you in fact you have sort of diminished your bank balance in some sense. Or equivalently, you can also think of another way. Let's say a resolution that you deem is excellent for some order moment, like the 10th order moment for this Reynolds number, which is very small. As you see, this is very nice, but as you go to higher Reynolds number, it's not even very high. 64 is trivial these days. You are already going deep into the region that you should resolve well. So the question is, at some point or the other, the thing is going to hit you. That is to say, you cannot a priori fix according to these simple calculations, simple demonstrations, what resolution you must have. Therefore, the question to ask is there a resolution that assures us that everything of consequence is resolved adequately? Okay, let's see if we can answer that. So I'm afraid I have to use this here. I didn't have time to make all this thing there. So now let's go to structure functions again. I have here the part that is analytic, which goes like r to the power n here, this one here, and then you have the part in the inertial range which may go like r to the power zeta n. And let's say you have a crossover point here, and what you have to do is you have at least got to resolve a little bit below into the crossover region in order for you to get the derivatives right. If you cross over into that region, you are reasonably okay. So grid resolution up to a fraction of this crossover scale assures us that the velocity field is adequately resolved for our purpose. So let's say I go to a different order moment. First, let us look at some mth order moment, which is what I have shown here, and then another moment where n is greater than m, which might do that. It will go like r to the power 2n and then r to the power zeta 2n there. And if it turns out that the crossover point for these moments, all these moments is the same, then, and they will all, if they are the same, and they will all turn out to be of the order Kolmogorov scale, and then you resolve up to Kolmogorov scale or a fraction of it, you are doing very well. Then there is no problem at all. On the other hand, if the circumstances are such that for low order moment the situation is such, for high order moment the situation is such, and the crossover scales really in fact decrease, become smaller and smaller as you go to higher and higher order moments, then clearly there is no one fixed scale that you would have to use for all moments, and then you would have to know which moment you want to get right, and therefore that determines for you the accuracy of the thing. So each order moment requires its own resolution in some sense. Or let's take this a little bit further. If I plot this eta 2n, that is the resolution scale that is required for 2nth order moment, as a fraction of this integral length scale, and plot it against 2n, of course, when n is 1, that is you are at the second order moment, resolve it at the Kolmogorov scale, which is drawn here, that would be fine. But if you want to be more and more ambitious, you will have to get lower and lower in scale, and the question is there an asymptote eta infinity that is finite and okay for all orders, so to speak. Of course, for that one needs a bit of theory here. One needs to know how to get this eta 2n as a function of n, and here I will skip a lot of the theoretical part, but basically tell you what the result is. In fact, here is the reference that you can find this in. It turns out that you can write an expression for eta 2n divided by L, which is a function of Reynolds number raised to this exponent here, 2nth order exponent, 2n plus 1th order exponent minus 1. So if it is true that you have zeta n going like n, zeta n goes like with n according to this kind of thing, we think we know this for certain at the moment. At the moment, our confidence is that there is a curve like that, and the curve probably saturates eventually, although we really don't have any good evidence for that. Presumably, with this zeta 2n as n approaches very large value is the same as zeta 2n plus 1. That is to say, this and this will cancel out, and you have Reynolds number to the power minus 1 there. So, if whatever I have said so far is correct, then eta infinity, that is the scale that you have to resolve in order to get all the moments right as a fraction of L, would go like Reynolds number to the power minus 1, and not as Kolmogorov scale would do Reynolds number to the power 3/4. Okay, so this in fact what I have here in that particular graph is the same thing. This graph here plotted in a different way. This eta 2n as a fraction of L is going like Reynolds number to the power c of n, and if you believe the theory, this would be the expression, but never mind, I can always take it from empirical data and so on, but it's not going to be that different. But basically it says if you are at very low orders, what you have to have is c 2n is minus 3/4, which will tell you that resolving Kolmogorov scale is fine, but you go to higher and higher orders, it will go to Reynolds number to the power minus 1 eventually. So, it has a very practical consequence and a very important theoretical consequence, and I would like to make a mention of both of them in the few minutes I have. The practical consequence is that instead of having Reynolds number, microscale Reynolds number going like n to the power 2/3, when n is the number of grid points on the box, you will end up with having a relation which is that the Reynolds number goes like n to the power half. Now, this is a big difference between half and 2/3, and just following it up, the computational work that is required for a given Reynolds number does not go any longer as Reynolds number to the power 3, as is the case for the traditional estimate using Landau-Lifshitz estimate for the number of degrees of freedom, but it will be Reynolds number to the power 4. And therefore, if all of this is right again, the ratio of the present estimate to the traditional estimate, which goes like Reynolds number to the power unity, the computational work, for R lambda of 1000, where Re is of this order, the ratio is a very large number. So, in fact, the computational work required would be a lot larger. And if again you want to resolve up to eta infinity, whether that is needed or not for the purposes one has so far is not an issue, then instead of 1200 as one would imagine, you would only be able to get that far. Or as I said in the petaflop machine, that perhaps if you stuck to eta k Kolmogorov scale, you would have been able to resolve Reynolds number up to 4000, as I said, but you can only go up to 800 or so, and that I think is probably not going to be enough even for sorts of things we are considering. Okay, so that's a practical consequence. On the other hand, it is not enough just to say, well, you really have to resolve everything under the sun, but you have to have some idea of the error you incur if you do not resolve all the stuff. Okay, so that's really important for any practical consequence. So, I have here a calculation that tells you how you can estimate the error for any fixed resolution. So, it proceeds very simply that the derivative one calculates by taking velocity difference between 2 points and divide by the distance between the two. And of course, as the distance between the two approaches, you have the derivative. But for any finite separation between the 2 points, you can expand it by Taylor series using these next order terms. And from here, you can write the difference between the actual derivative, the 2pth power of the actual derivative, minus the 2pth power of the estimated derivative, normalized this way, and it turns out to be quite simple depending on p here and this statistical quantity. The only assumption used there is the homogeneity of the field, and nothing else has been used. Now, here you want to estimate this quantity. What you might do is, if a second derivative is the first derivative divided by the separation distance. Eta is no longer a fixed quantity, but it is a variable, a field quantity. That is, at each point you have to choose a different number, so to speak. And when you do that, this kind of product, average product, turns out to be Vx to the power p, not divided by eta squared, where eta would have been a fixed number in the field, by eta 2 squared, because you have a second derivative here. So, it is a second order quantity. This is a standard thing that one might do in field theory, for instance. So, basically, if you fix all that, what you will end up with is that this normalized difference, depending on the order of the moment like this, and the separation distance divided by the second order, the resolution distance for the second order squared. Or if eta 2 is the standard Kolmogorov scale, which goes like Reynolds number to the power 3/4, it's a very simple simple formula you can write down. Or for general things, I have given here a recipe which will depend on zeta 2 alone and order of the moment here and the Reynolds number. So, this formula actually tells you, if you tell me what the resolution is that you are using as a multiple of the Kolmogorov scale, and ask me what is the order of the moment, or tell me this is the order of the moment, and ask me what is the error that I commit by resolving with delta x, I can tell you that is the number to use. Okay, so that's actually, I think, very useful. But let me now say what the theoretical consequence of the sort of considerations I have presented for you are. I will not go into this too deeply either, but very simply, there is a relation between the velocity differences and the dissipation in Kolmogorov's refined similarity hypothesis. This is a kind of miraculous result, which one doesn't know why one should expect, but roughly speaking, there is a certain limiting process involved here. But without taking it through all this, the dissipation rate is related to the velocity derivatives at some scale eta, for instance, Kolmogorov scale. The third power of that, in front of which resides a stochastic quantity that is supposed to be universal. So, this is the refined similarity hypothesis of Kolmogorov, 1962, and this has been used any number of times in the literature, including by me. I have spent some years trying to see if this is right or not. If I take with the present considerations, epsilon is the limit as r tends to eta now, that is, I take it down to the smallest possible scale of interest of this quantity here, viscosity times the gradient of the velocity divided by r squared. And now, the eta here, the local eta, is such that if I take the velocity difference across that scale, the Reynolds number on that basis has to be locally unity. It is not a global quantity that as one has thought about all the time. So, this will mean that there is a relation between the velocity increment and the distance of separation between the two, so that the Reynolds number is of order unity. And you put that in here, what I actually find then is that the velocity difference scales not like the third power of the the energy dissipation doesn't scale like the third power of the velocity differences in Kolmogorov, but are the fourth power of the velocity difference. Actually, one thinks that this is such a zeroth order type of difference that you must be able to pick out from simulations very easily. But actually, that is not so, because there are very few simulations that get you the epsilon and the moments of that to the order of accuracy that is required in order to measure different moments of this, which is what will only tell you eventually whether the present one is right or the refined similarity hypothesis is right. So, efforts have been made in this direction, and I simply give you what efforts have been made without being conclusive. So, as far as we know, the only measurements, only simulations that have been made to resolve all these scales right in order to get moments of order, even of order 4 of the energy dissipation right. You see, if my analysis is right, to get the fourth power of the energy dissipation, I have to get the 16th moment of the velocity difference, you see, because they are related to each other by a factor, by power of 4, unlike the Kolmographs, which would be 12th power, but there is a difference between 12 and 16. So there are data here. Already we are not sure of this. We are reasonably sure we have the second order and the third order moment, right? But now these moments are too low for me to be sure that in fact we can differentiate between the Kolmograph and the present one. So basically here is data for you. The exponent here for the moments of the energy dissipation, this is what one measures. This is the present one, and this is the error bar on this. So they are sort of comparable to, but still not conclusive enough. So what's the point of my talk? This is my last slide. The point of my talk is the gain in computing power translates to weaker gains in the Reynolds number than previously thought. I think one should be aware of this for sure, and simulations have to pay some attention to it. The constraint becomes stronger with increasing Reynolds number and increasing R to the moment. There is not much difference between Reynolds number 3/4 and Reynolds number 1. If Reynolds number is of the order unity, they are the same. But the higher you go, the gap becomes larger and larger. This constraint also makes a large difference for studying extreme events. Also in other contexts of PDFs of tails I have shown you, intermittent processes in combustion. And the criteria of the theory could be softened for finite order moments at finite Reynolds numbers, and I provided some error bars for these things. Thank you so much.
I want to cheer you up a little bit. You write asymptotically for large n and for large Reynolds number, but when you consider finite Reynolds number, you don't need infinite number of n, because you can only resolve finite number of n, which depends on Reynolds number, because you eat inertial interval also from, which means that it's a little bit better that you would.
Yeah. I have not denied that. I have in fact said that all along in some sense. This is my contribution to saying what kind of errors you make if your resolution is not as good as I'm saying one ought to have. And this tells you how, and that's why I spent some time getting that estimate.
Yeah, that's fine. Sreeni, could you please go back to that transparency where you had the granular stress in a channel?
Yes.
That transparency implies that the error in the mean profile is probably something like 10%, which is absolutely incredible, unless that is a finite, low order finite difference code with a uniform grid or something like that.
This was shown to you yesterday by Jörg Schumacher.
So I realize that.
And if Jörg is here,
no
he should answer this. But basically, that is, I have worked with him closely enough for long enough time that I take what he says to be true.
Well,
But we can
that
check on
I
this,
am
yeah.
sure it's not. I mean, unless
Okay,
the
all
code
right.
is very
Okay,
bad.
one more. Yeah.
I cannot unfortunately speak for this. I have not done the calculations myself.
A comment. I will rather a little
Brief.
more,
Brief. We run out of 5 minutes. Yeah. Oh, yeah, go ahead.
a little more pessimistic. That is, higher the moment exponent are not only sensitive to the resolution but also large scale condition. So if we get reliable exponent, then the prospect may be a little more pessimistic.
I am being not pessimistic, especially, but I'm saying one has to be aware of the problem.
Just realistic.
Okay.
I also am aware that this is the limiting situation.
Well, I was dropping because so many hands, but anyway, I have something to. Okay, there is a diagnostic which could be very good just to evaluate the quality of the resolution. How we make it or not. You just compute a Reynolds number, but which is based on the wavelet representation, which means you compute a local Reynolds number in each position in space, and then if you are below, very low Reynolds number, below 1, let's say, then you are sure to be in the dissipative range. If you are above it, you are not in the you are still having some non-linearities. And then, and in a paper for CTR 1990 with Charles Menvaux, what we did, we took the data set of Kim and Moy, and we compute this Reynolds number, and we showed that, of course, Kolmogorov scale, it's only an average scale, and the variability around it, the spatial variability, is huge, and that means you don't resolve well enough. We have already said that 20 years ago. 50
I
years
think
ago.
you could devise different measures of how well you have resolved. I am giving you what I regard as the simplest measure, very easy to understand in principle.
This one is very simple to compute, and it's natural, because are we resolving the nonlinearity well enough?
Could be, yeah.
Okay. Oh, since he's, yeah, go ahead. He's still, are you ready? Okay. Toshi, yeah.
Just one comment I told you yesterday. So the argument about the slow crossover length seems to be looks like okay, but we need some caution. But you know, that kind of the business or the argument is if the level of the structure function the same, then when you go the higher order moments, the analytic path is goes this way. But still,
whatever you want.
the level of the amplitude the same, you may the crossover length become smaller. But the amplitude of the structure function itself depends on the order. It's an increase in amplitude. Therefore, we need some.
Okay.
But Yuki, I'm Toshi, this is very simple to answer, but I will not take the time to answer.
Thank you, Sreeni.